So you probably did this last semester or in Calc 1, I would hope. But so this is a really, really, really simple differential equation. And a differential equation is just basically an equation involving a function and its derivatives. So it could be a first derivative, second derivative, third derivative. But so this right here, so thinking of t as time, and why don't we, I think to give this a little bit more context, let's, instead of y, let's use p. Just to give it a little bit more context. So imagine that p represents population and t represents time. Okay? Okay. So what does this say right here? Like if you were going to read that in a sentence, what would that tell you? Yeah, the rate of change of the population. Yeah, is equal to twice the whatever the population is at that point in time, right? So if you have 100 chickens that are there, right? So you have a certain rate of population growth. Would that be more? Would the chickens grow faster if there was 1,000 chickens as opposed to 100 chickens?
The rate may change, but yes, the number will grow faster.
Isn't the rate of change the same?
It would, right? Wouldn't so? All right. So imagine. Okay, let's make it even more drastic. So you have 2 chickens and you have 1,000 chickens. So on one side you have two chickens. Chickens, and over here you have 1,000 chickens times 1,000. Which population is going to grow faster? Yeah, definitely the one with 1,000 chickens. Okay, so all right. So anyways, so that's basically what this differential equation tells you. Does anybody remember how to solve this differential equation? It's very simple.
You multiply by dt.
Yeah, you move the dt over, right? So you have dp is equal to 2p dt, and you integrate both sides. Oh. So then you get that. So this one we well actually the today is not my day, is it? The you wouldn't have done this in Calc 1. Not this way, anyways. Well, it depends. Well, no, not like this. Anyways, I'm sorry. I don't know why. I am. Just today is not. But okay, let's not do it. I mean, we are going to do it this way later, but I that's not what I wanted to do. So think of it this way. So let me just ask you. So what is the function that the rate of change of the function is proportional to itself? There's one function that when you get the derivative of it, yeah, it's the exponential function, right? So the solution to this differential equation is it's an exponential function, right? Okay, but what I want is for when I get the derivative of this function, I want it to equal to 2 times itself, right? That's what this is saying. So here you're looking for the function that when you get the derivative of it, it equals to 2 times that same function. So what's missing here? 2. A 2, but where? Yeah, on top, right? Because what happens when you get the derivative of e to the 2t? It equals to itself times the number 2, right? Okay, and then there's a but there's a constant missing, right? Well, okay, we'll talk about that later because I'm already okay. So what I wanted to do is I wanted to go over some examples with sheets that I just gave you. Yeah. Okay, so this is just these are all things that we're kind of going to see. Different differential equations that we'll see, different situations that are modeled by differential equations. I just wanted to sort of give an overview of what we're going to be doing. So let me find these things real quick. I made a, where is it? Uno momento. Math 151. Oh my God. Seriously. Where is it? What is it? Oh, I know where it is. Sorry. No, I remember now. Oh my gosh. Stop it. Oh my God. Sorry. There it is. Okay. There we go. 1, 2, 3. Okay. All right, it opened. Whew. It opened. Thank goodness. It opened. Okay, all right. So this is the first one that you guys have, right? So the first one is you've got a. So this is one of the applications that we have. So we have a tank filled with water, right? So this tank. What happens? So let's take a look at the. So this is the differential equation. And we'll see where it comes from and all that kind of good stuff. But so this is the differential equation. And then this right here is called a slope field or a direction field. So what do you guys think these little arrows represent? Yeah, they're the slopes of basically the slopes of the solution to the differential equation. So, like right here, for example, what does the dy over dt represent? So if you read the problem, it says water drains through a hole, and then determine so water level y of t at time t seconds. So y represents the water level, right? T is seconds. So dy over dt is the rate at which the water is exiting. Right? So if you look at this, so what do you notice about the slope? So like right here, for example, if I mark that point right there, what would you say that represents right here?
Full tank of water.
So so 50, let's say in this case 50 feet, right? So imagine the water level in this case would be 50 feet, right? And so initially, what do you notice about the rate at which the water goes out? Yeah, it's steep, right? But down here, what do you notice about the... Yeah, not as fast, right? Which makes sense, right? So you have a full tank of water. The water comes down really fast at the beginning, and then as it gets empty, then it starts going out a lot slower, you know? So back in the day when you had, you know, the big tanks, or if you lived in another country where we don't have these fancy pumps, you would notice the situation. You know, your tank gets emptied, and then the shower, and sometimes it runs out. You know, bad stuff. You get full. You're full of soap, and you have to bring in a bucket. And anyways, okay. So all right. So let's do a little. So this is this right here. These are called solution curves. So they represent particular solutions of the differential equation. So remember that a solution is a function. So this is the particular solution. For example, if you had a tank that started at 50 feet in a water level. And so what does this line describe?
The fastest rate.
The total time.
The water level.
Yeah, the water level. So this represents the water level given the time. This function right here, which has a particular equation, so that would give you the water level given the time. So that's what a solution to the differential equation would be. So you have the differential equation that tells you the rate of change at any particular point in time, and so the solution to that would be the function that tells you the water level at any particular point in time. Does that make sense? So you have information about the rate, and you find the function that gives you the water level. Thumbs up for the idea? So like right here, for example, what does this solution curve represent? The second one.
When it's at 30.
Yeah, the water level starts at 30 feet, right? And then you go down, and then eventually it runs out. Okay. So any questions about that particular model? No?
Are they proportional though? Like for each? I don't know.
Well, it depends, right? So like if your tank starts off, so let's say I change one of these. Let's say I make this instead of 30. Let's make this one 10. What? Seriously? What in the world am I? What the? Oh my gosh.
Control C.
Yeah, Control Z doesn't work though, and what? Seriously? Oh my God. Why is this? This is like the worst day ever for.
We got a PC.
Okay, well I guess apparently I can't show you because it doesn't want to.
That's fine.
All right. Sorry. Okay, now the second one. So this model, notice it's called coffee because it represents the. So this is on your second page. So this is. Let me actually bring it up here so that. Okay, so this is this one. So you have a coffee cup, and it starts off 90 degrees. You put it inside a 30-degree room. The cooling constant is 0.1 minutes to the -1, and then so this differential equation models the rate of change of the temperature of the cup, right? Okay, so what you want to do is you want to find, so this tells you the rate of change of the cup. So you want to find, okay, well, what's the temperature of the cup at a particular point in time? So if we go back, so let's go over here. So let's hope that it works out here. So what does that represent? the solution curve that I just drew.
Yeah,
That's
the
the
shares
temperature
are going
of the
towards 30 degrees.
So what
Temperature
we'll
was just telling.
That's the temperature of the coffee.
so my coffee cup started off at 60 degrees, right? So that was that's called the, does anybody know? Initial condition. Initial condition, okay. So coffee cup started at 60 degrees, and then it decreases. But why does it level out right here at around 30 something or other? Yeah, this is the temperature of the room, right? So the temperature of the room was, I think it was 38, was it?
30.
Oh, 30, okay. So it's going towards 30 degrees. What do these represent down here?
Well, actually, those are
Colder than the room, so that one is heating up to the temperature of the room. So you can, kind of draw a solution curve going there, right? So just for fun to see if this works. No. Totally broken, my program here. Okay, anyways, on to the next one. All right, let's take a look here. So the next one we've got, and so again, these are all things that we're going to look at more in depth. We're just kind of going through and seeing what we're actually doing, because I think it's kind of hard to see if you don't really know. So you've got a skydiver jumps out of an airplane, and this tells you the velocity of the skydiver. And so what do you notice here is happening with our little model here for our skydiver? So when you go down, do you just keep going? So of course, you start at a certain velocity, right? Usually pretty close to 0, right? And then you go down, well, you start going down fast, right? You go fast, 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 fast. But what do you notice happens?
Try your most to the ground, you still have pressure.
Air resistance kicks in, you hit terminal velocity.
Yeah, you hit terminal velocity at some point, right? Where you can't go faster than, in this case, it looks to be around negative 100, right? Is it miles per hour? I don't know. Whatever. Yeah, I think it was miles per hour. Or feet per second. But,
Kilograms.
right, because of drag, right? So, what was it? It depends on what the units were.
You got 9.3 grams.
Yeah, meters per second. Okay. Yeah.
So if down is plus x, or plus y rather, wouldn't you be increasing the velocity? How do you go from a positive velocity to a negative?
Well, negative velocity means that you're going down.
Just
Yeah. Because it means that your distance is decreasing. Distance traveled. And then the same thing, notice how, if like, for example, if you were, so what does this represent? Right here.
If you were getting shot upward or something. Yeah.
If you were shot.
Upward.
So what would it represent? Where would I start if I were just like jumping out of an airplane? Like
0.
pretty close to 0, right? Because you jump out of an airplane, so you're like, oh, 0 velocity. And then you start going down, and then you get to 100, negative 100-ish, let's say. But what would this represent up here, 300?
atmospheric from like the shuttle, space shuttle or something crazy. I don't know.
No, it would be like you getting shot, but not shot down. In this case, this would be shot up, right? Because your velocity, because remember again, this is rate of change, right? So you get shot and then you go down, right? Your velocity eventually starts going down, and but what about right here?
So if we already been falling 0 and then go back. You're shot down. So
Yeah, shut down, right? So imagine, this is not realistic, right? You're already jumping out of an American plane. Do you really want to get shot again, right? But, even if you're shot at a super fast speed down, drag eventually takes you, back, you would go slower in a way, right?
There's like ejection seats depending upon the angle.
Yeah?
Well,
Okay, ejection seats, there you go. See?
So y of t is the velocity.
Yeah, if you're inverted.
Well, in this case, it's v of t, but yeah.
Wow, this one is y.
Okay. All right. Next. See, applications galore. Look at this. This is like the never-ending applications of differential equations. So you have. So this is. Remember the one that when we were talking about chickens and we were talking about this, right? So what do you notice about this population growth model that is interesting? No, it is interesting because
That it'll,
Exponential.
that 1,000, the population of 1,000 is.
okay. Imagine you have a chicken coop and you have 1,000 chickens, right? Okay, and the chickens are breeding and breeding and breeding and breeding. What does this assume?
Is that
Never
the
stop.
is constant? Like
They
all
can-
these elements are constant?
There's no
Oh, it's assuming that there's no, yeah.
Right. This is assuming that you can continually breed chickens, and these chickens will all live happily ever after in this space that even if they're bursting out of the seams, they'll still just keep growing and growing, right? So this is called, in case you're interested, this is called Malthusian Growth. This is back in the day, back in the I forgot what century this was. So this guy was saying that one day the world will just explode because the population is just going to continue to grow exponentially, and it'll just completely be overcome with people and
Carrying capacity.
and we're all going to die. Yes. You're right. He did not consider, that after a certain point, you can't put any more chickens in a chicken coop, basically, right?
That was
Yeah.
whole movie.
You didn't foresee agricultural techniques that increase the carrying capacity. We still
But even then, you can only fit so many.
Yeah.
I mean,
I
even
haven't
with
hit that yet.
how do you know that?
whatever
How do you know
agricultural
that?
We'll find out
techniques.
soon.
But anyways,
Little oil like that.
back to the task at hand. So this is a population growth model. It's called Logistic Growth, and so it assumes that it has a carrying capacity. So there's a limit to, in this case, how many deer can live in this forest. So you've got this factor right here that limits the growth there, and so let's take a look at this because this one's pretty interesting. So since I can't do any fun drawing curves here, so let's talk a little bit about because there are several different areas, right? So like I've got up here, let's say. So what does this mean?
Yeah.
So way too many deer. So this is like, you throw in, so this forest has 1,000 deer carrying capacity. You throw in 2,000. Well, what happens? Well, the population decreases, right, to
Right down to 1,000.
equal to 1,000. So then, if you have a couple, then this growth. So notice what do you notice about the slope of the what do you notice about the growth in the beginning?
Slow.
So slope, and then
It speeds up.
speeds up, right? But then as you get closer to the carrying capacity, it starts slowing down again, right? Does that make sense? And then, what do you notice down here? Yeah, so it goes down. So anything below 0 is going to go down to negative infinity, it looks like, right? But in the context of what we're talking about, deer, can you have negative deer?
Not really.
No, right? So this is not applicable to the particular situation, that physical situation that we're talking about. So we, when we're modeling this, we kind of ignore that bottom part there. But, we consider it when we're studying it, but we don't, take it into account. It's negative deer. That doesn't make sense. All right. I think we've got one more. What's the other one? One more to take a look at. One, two more. So this one actually is pretty much identical. It's just U.S. population. Assume the carrying capacity is 500 million people, which, getting there. But it's identical, right? So actually, let's just skip that one for now, because it's identical to the deer. All right, so this next one is, we've got a rumor that spreads through a small town. And then y of t is the fraction of the population that has heard the rumor at time t. And so you've got this model, again, which is a logistic model. And so you've got this so let me hit play here at least, because I set it up to play, so might as well hit the button. So what's going on here? So the model is similar to the other one, right? So again, when it's negative, it goes down to negative infinity. But does that matter?
No.
No. So what happens here with the? What is this describing?
The rate at which it's spreading.
Yeah, the rumor, right? So what is the number 1? What does that represent?
100%.
100%, right? So this 1 is 100% of the people in the town have heard about the rumor, right? So you've got right here, I think it's 1/10, right? So the rumor quickly spreads, and then when everybody knows about it, well, then the last few kind of takes a while, right? For the last few, it's like, oh, you never heard about that?
Yeah. They come into Walmart this week. They heard it.
That's horrible.
All right, questions? So that's what we're going to be doing for the next few days, couple days, 2, 3 days. All right, take a break. You what? You left your jacket.